In this video in our Chemistry of the P-Block series, we're going to take a look at the Group 4 chlorides. So we're revisiting Group 4 again here, and once again we are going to look at the striking difference between compounds formed by elements at the top of the group, namely carbon forming carbon tetrachloride, with other elements further down the group, namely in this case silicon forming silicon tetrachloride. And there's a big difference in the behavior of the compounds of these two elements. And again, we're seeing this big disparity between the top of group 4 and the bottom of group 4. So let's jump into this and have a look and see what's going on. So if we start looking at carbon tetrachloride, then CCl4, look at the orbitals for carbon. I've ignored the 1s orbital here because that's an inner shell and doesn't engage in any bonding. So carbon's element number 6 is going to have 2 electrons in the 2s and 2 electrons in the 2p. Now, just as we've seen several times already in this series of videos, in order to form 4 covalent bonds, carbon has to excite an electron from the 2s to the 2p. So there she goes. Now it's in a position where it can form 4 covalent bonds. So if we were back in GCSE days drawing dot cross diagrams, we'd probably draw carbon looking a bit like this, and we'd start putting our electrons from the chlorine to come in here. So there's 1 electron into the 2s. Here's another electron coming into the 2p from another chlorine atom. A third chlorine atom will come in, and a fourth one will come in. And now carbon has a full octet. It's a nice stable situation. And it's obeying our octet rule. Now, carbon tetrachloride here now is a very unreactive material. This is a very stable compound and it does not react with water. So it looks a lot like water. It's a very heavy liquid. All these chlorine atoms give it a lot of weight. And so if you were to add it to water, the two liquids would not mix. In fact, water is a lighter liquid than carbon tetrachloride and would float on top of the CCl4. No reaction between them would occur. Now, the reason for this is these orbitals here, the 3s and the 3p, are not available for bonding for carbon. In order for carbon to react with the water, electrons would have to come in from the water and we'd need to undergo octet expansion. Carbon would have to accommodate more electrons. It's got nowhere to put them. These 3s and 3p orbitals, the next ones along, are in a different energy level to the 2s and the 2p. I've tried to show this here with a significant gap between these two orbitals. Because of the big energy gap here, these are not available for bonding, so carbon can't expand its octet, and so it can't react with water. It's a very different situation, though, to silicon tetrachloride, SiCl4. Now, if we look at silicon's electron configuration, it's 1 period down from carbon, so now we're dealing with a 3s, 3p, and a 3d orbital now. So remember, there's no such thing as a 2d orbital in carbon. So now we have an extra orbital here in silicon which didn't have in carbon. So if you start filling in the electrons, we've obviously ignored the 1s2, 2s2, 2p6. We're going from 3s2 here, silicon, 2 electrons in the 3s, 2 electrons in the 3p. In order to form 4 covalent bonds, to bond with the chlorine, we need to do the same excitation of the electron from the 3s to the 3p that we saw in carbon. And now we've got that situation where we've got 4 electrons surrounding our silicon atom. And we can bring in our chlorine atoms here. So there's 1. I've neglected to put the other electrons around for the chlorine here, but we would have another 6 electrons obviously there as dots. We'd have another chlorine coming in here and pairing up with the 3p, and the third, and the fourth. And we have silicon tetrachloride. Now, this material, though, reacts quickly with water, unlike CCl4. The reason being is that silicon can undergo octet expansion. The 3d orbital here now is close enough in energy to the 3p for it to be available for bonding. And so what can happen here is that a water molecule can come in. Obviously, it's got 2 unpaired electrons on its oxygen. I've just shown 1 here. And it can coordinate those electrons to the silicon. The electron pair, these are the ones from oxygen and water, going into the 3d orbital. Carbon had nowhere to put those electrons, so could not react with water. In fact, we can get a second water molecule in there as well. And that can coordinate in there. Now you might ask yourself, well, why aren't we getting more water molecules coming in? Because we've got other 3D orbitals here. And I'm guessing the answer to that is there's just not enough room now around the silicon. Now we've got effectively 6 bonds to the silicon here. I should imagine there's not enough room for any other water molecules to come in. As soon as that intermediate is formed, it'll break down. And it'll break down to give us fumes, misty fumes of HCl. So that's one thing we see. We see like these fumes of HCl coming off the reaction. And we also form a white precipitate of silicon dioxide. And so we can show that breaking down. The H's and the Cl's will get together. And there's our equation then for HCl molecules. Here they are. And silicon dioxide, here it is. So the reaction of water with group 4 chlorides. You only need to really look at 2 of them. Carbon tetrachloride at the top of the group doesn't do anything with water because it can't expand its octet. Silicon tetrachloride, just 1 period down, reacts quickly with water because it's got 3D orbitals where it can include water's electrons, form an intermediate, it can expand its octet, form an intermediate, and that intermediate then can break down to give us our products. Okay, this is again a common question coming up on the exam papers, so make sure you fill in your booklets on this, have a go at some questions. You'll find several of them on the past papers and the other questions which we give you.